Welcome everyone. Today we shall study the symmetry property of DFT. The concept of symmetry property of DFT says that the symmetry property of DFT states that the frequency domain samples exhibit the mirror-like relationship that depends on whether the time domain signal is real or even or odd or imaginary. So for the real signals, the DFT shows unique conjugate symmetry. So half of the samples are unique. So here you can see that the complex exponential in the DFT contains cosine and the sine waveform. As we know that the even function or the even waveform will always be cosine and the sine will be always be odd function. So even parts of the signal interact with the cosine and the product and produces a real and the even components. The odd parts of the signal interact with the sine function and produces the imaginary or the odd components. The DFT simplifies and reflects the natural symmetry of the cosine and sine function. So let us come to the property now. So this property will be asked for about 6 to 7 marks in the examination. You have to state the property which you are seeing on the screen. You have to state the property which says that if x of n is tends to DFT of x of n is x of k, and let us assume x of n and x of k are the complex valued or imaginary and real values. Let us assume that x of n, the signal input signal, have real part and the imaginary part. So DFT of x of n will be x of k, so that the let us assume that it is also having real part and complex part. So we get x of n and x of k is equal to xr of k plus j of xi of k. So this represents equation 1 and 2. We know that x of k is equal to a summation of n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi kn. So this is normal DFT equation. So let us write the equation with respect to the complex variables. Now we are writing the DFT equation with respect to the complex imaginary and the real values. So for x of k we are writing xr of k plus j into xi of k is equal to, then summation in the x of n place we will replace the real and imaginary parts, and e to the e component, this e to the power of minus j 2 pi by n into kn will remains the same. So let us multiply, let us expand e to the power of minus j 2 pi by kn, 2 pi by n into kn. So it is the formula, it is Euler's formula, it is a very common. You need to remember that e to the power of minus j sin theta, the formula will be cos theta minus j sin theta. So this is the expansion of the formula. So e to the power of minus j 2 pi by n kn will be represented as cos 2 pi by n kn minus j sin 2 pi by n kn. So this component and this component we will multiply. So when you multiply this and this, you will get these four terms. XR of n, two real terms and two imaginary terms. So now summation of n is equal to 0, n minus to n minus 1. The first XR of n into cos of 2 pi by n kn, this will remain the same, minus j XR of n sin 2 pi by n kn plus j xi of n cos of 2 pi by n into kn minus j into j. Here you have j into j. We all know that. So we know that j into j square will be minus 1. So substituting the value minus 1 here, you will get minus of minus 1 xi of n into sin of 2 pi by n into kn. So again simplifying the same equation, we get xr of n cos of 2 pi by n. This term will remain the same. Next, this term minus j xr of n sin 2 pi by n kn. This term will remain the same. Then this term will be xi of n cos of 2 pi by n. This term will remain the same. Plus here you will get minus into minus plus xi of n sin of 2 pi by n. So for after further simplification, we get here two components. So we are again further simplifying the same summation equation. So here we will get two components. Here one component with a will be x r of n cos of 2 pi by n kn plus x I of n sin of 2 pi by n kn. So here you will get real part and imaginary part. So how do you consider real and imaginary part? The here x r of n real part cos 2 pi by n into kn plus x I of n sin of 2 pi by n kn. So this is x r of n, x I of n. You both will be considered as a real part minus j. You will take minus j as common here. So this equation will be reduction of the previous equation. So here you are taking minus j common. Minus j where we are taking common, so that if you multiply this minus j to the component, you will get this equation. When you take minus j as common, you will get as minus j of x r of n sin of 2 pi by n kn. Minus into minus will be plus. This will be this component xi of n cos of 2 pi by n kn. We are taking minus j as common, so that if you multiply the same equation, you should get the same. So let us consider as real and imaginary part, because this real part does not have j term and imaginary part have the j term. That's why we are considering as imaginary part. So let us write it as x r of k, this real part, and x I of k is equal to this imaginary part. So now we know that x of n is equal to 1 by n summation of k is equal to 0 to n minus 1 x of k e to the power of j 2 pi by n k, and this is normal IDFT equation. Now we are writing an IDFT equation, and then what we are doing is we are substituting x of n with a real part and imaginary part, and x of k with a real part and imaginary part. So first we have taken the DFT equation and we have substituted real part and imaginary part. Again now we are taking IDFT equation and we are considering real part and imaginary part. So now you will get 1 divided by n summation of x r of k plus j x I of k into e to the power of theta. E to the power of, that is Euler's formula, e to the power of theta is equal to cos theta plus j sin theta. So cos of 2 pi by n kn plus j sin of 2 pi by n kn. So then we will multiply this whole term and this term. So you have to multiply with each other these four terms. So finally when you multiply these four terms, you will get this equation. When you get this equation, so wherever you get j square, j into j, you have to substitute it as minus 1. So now 1 by n summation of k is equal to 0. You will get, when you multiply, you will get this equation. Now we have to reduce the equation. X r of k cos of 2 pi by n kn minus xi of k sin of 2 pi by n kn plus j of x r of k sin of 2 pi by n kn plus xi of k cos of 2 pi by n kn. So now you have reduced the equation and we have taken j as common factor in four terms. After multiplying the two terms, you will get the four terms. In the previous slide you have seen. Now what you have to do is, now you are taking j common, so that you got now one real part and imaginary part. Real part is one where you have the where you don't have the j term. Imaginary part is when which part of the equation have the j term, that is the imaginary part. So we get x r of k and x I of k, x r of n and x I of n. So these are the two equations. We divide into two parts. One is real part and one is imaginary part. Now let us recall the equation 3. X of k is equal to this part where you have taken minus j as common. Recall the equation 3. So here you get real and even sequences where x of n and xi of n is equal to 0. So xi of x of n is equal to xr of n. That means real part does not have imaginary part. In this equation, real part does not have a imaginary component, that is j component is not there in the real part. That's why xi of n will become 0. So x of n is equal to xr of n. So make xi of n is equal to 0 in the equation 3. In the equation 3, you are cancelling the j part. So you will remain on, you will be having here, we take only real and even, but sign is not even signal, so it cancels. Okay, so now we are left with the x of k is equal to summation of n is equal to 0 to n minus 1 x of n into cos of 2 pi by n into kn. This is the DFT equation. This is the DFT for the real and even sequence. Now real and odd sequence. We all know that sine function is the odd function. Here we are maintaining xi of n is equal to 0, real function and odd function. For real function, real sequence, always the imaginary part will be 0. So we will be considering only the real part. When you consider the real part, the cosine is even. We are considering is real and odd. We should consider only odd function. The sine function is only odd function. Cosine function will always be even function of a signal. So you will left with the real and odd means you will left with the no imaginary part and also with the sine function. Third is purely imaginary part. When you have a purely imaginary part, that means the part of the equation where only j exists. Remaining the real part will become 0. So recalling the equation 3, we have to substitute the real part xr of n is equal to 0 and we consider only x of n is equal to j part, that is imaginary part. So you will get this equation. Here we consider this as x of n. So in the real part xr of k is equal to summation of n is equal to 0 to n minus 1 x of n into sine of 2 pi by n kn, and xi of imaginary is equal to summation of n is equal to 0 to n minus 1 x of n into cos of 2 pi by n into kn. So this explains the property, symmetry property of the DFT, where we will deal with the three cases, that is real and even, real and odd, and purely imaginary. So we create three cases in the property. So this is the proof of symmetry property of discrete Fourier transforms. Thank you.